welcome back. This is Chapter 7, Video 2, where we'll be discussing PD derivations, specifically the rules universal introduction and existential elimination. The next rule we'll look at is universal introduction. This is the first of the two more complicated rules, because unlike the previous two, the third and fourth have certain sorts of restrictions on them to make sure that we're making valid inferences and not coming up with potential falsehoods from the primary assumptions. I'll explain that in a little bit. If you look at this rule, it looks very much like existential introduction. If you have some formula that contains a constant, you can add a universal quantifier and replace that constant. This seems like it might be a bad idea, because if we had something like the following, Gregory is a philosopher, it seems like this form would allow us to replace the constant with a variable and universal quantifier to get everyone is a philosopher. But clearly this is a fallacy. While it's true that I am a philosopher, it's clearly false that everyone is a philosopher. In fact, this is essentially an overgeneralization or hasty generalization. That is, you can't make a fully general conclusion from just a particular example. There's no guarantee that it won't lead you astray, as we see in this case, leading from a truth to a falsehood. So why do we have a rule form that allows us to do it? Well, it doesn't allow us to do it in all situations. It only allows us to do it given that certain conditions are met. First, the constant we replace cannot occur in an undischarged assumption. I'll illustrate that in a minute. And the constant that we replace can't occur in the result. I'll illustrate that also in a minute. Let's see a situation in which this rule works, and then eventually we'll talk about how to avoid violating these restrictions and why these restrictions are important. So what we want to see is a case where we can go from a particular instance to a generalization without making this mistake. So consider this argument. All philosophers are strange. All strange people are annoying. This is a fairly straightforward universal syllogism, and the conclusion may seem obvious to you. Let's write it out. All philosophers are annoying, which is probably false, but not because the inference is invalid, but because it's unsound. Now, this is an inference that may seem pretty obvious, but because we want every step along the way to be painfully obvious, we need to see how it would work in our derivation system. So let's relocate the conclusion farther down the screen. Now, remember that our quantificational derivation rules only deal with the quantifiers themselves and don't allow us to make sentential inferences. So in order to do anything interesting with our premises 1 and 2, we need to get rid of the quantifiers in favor of some names or constants. We obviously can do that with something like universal elimination. From line 1, if all philosophers are strange, then in particular, if Bill is a philosopher, then Bill is strange. And in particular, I'll squeeze 1 in parentheses there as the citation for where that's from. And from 2, in particular, if all strange people are annoying, then that goes for Bill as well. So 2 natural language instances of what we in our derivation system call universal elimination. Now, given lines 3 and 4, we don't actually know anything in particular about Bill. Just if he's a philosopher, then he's strange, according to line 1, and if he's strange, then Bill is annoying, according to line 2. But we don't actually know anything about this Bill or who he is. So I want to emphasize this point. We don't have any special knowledge about Bill. But let's make an assumption. Suppose Bill is a philosopher. Literally, just for the sake of argument, we're going to suppose that. That's essentially an auxiliary assumption. That's why I've indented it. Well, given 3 and 5, then Bill is strange. But given that Bill is strange, and line 4 tells us that if Bill is strange, then Bill is annoying, we get Bill is annoying from 4 and 6. Now, what we've just proved in 5 through 7 is that if Bill is a philosopher, Bill is annoying. So let's outdent, since we're dispensing with the assumption in line 5, and generate the conditional. If Bill is a philosopher, then Bill is annoying. That's going to be 5 through 7, which is essentially an arrow or conditional introduction move. Now take a look at what's happened here. What role do specific claims about Bill play? 3 and 4 are conditional claims, so don't actually tell us anything specific about Bill. And 8 is also a conditional claim and doesn't tell us anything specific about Bill. In line 5, we did suppose something specific about Bill and drew 2 further specific subconclusions. But when we go to create the conditional in line 8, we dispense with those special assumptions. And so 8, again, doesn't tell us anything specific about Bill. In fact, if we wanted to, we could have used any name in place of Bill throughout here, and the pattern of inference would have worked just the same. So what 8 tells us isn't simply about Bill. We don't actually care about Bill. The name Bill was just a placeholder for the pattern of inference. So what's said in 8 applies not just to Bill, but to anyone at all. And so that allows us to conclude that all philosophers are annoying. Or for any person, if that person is a philosopher, then that person is annoying. Now let's see how this works with respect to the rule. First of all, take a look at the restrictions. The constant in the English version of this argument is Bill. And what are our undischarged assumptions? Those would be the initial premises or primary assumptions. Bill does not appear in those. And Bill cannot occur in the final quantificational claim. That would be line 9 here. And Bill does not appear there. We replace both instances of Bill from line 8 when we move to line 9. So, thinking of this informally, we've met both of what will be our formal restrictions. And so in this case, it's okay to go from a single instance to a universal quantification. We don't make the hasty generalization fallacy. Let's see how this works symbolically. So a symbolized version of the previous argument would look like this. So we have the 2 premises symbolized as primary assumptions here. All x px then sx for all philosophers are strange. All y sy then ay for all strange people are annoying. And our goal, all x px then ax for all philosophers are annoying. Now if we follow the exact pattern we used earlier, we got lines 3 and 4 by putting the name Bill in. So we would get p lowercase b, the constant for Bill, let's say, pb arrow sb from 1 universal elimination, and then sb arrow ab from 2 universal elimination. Now some of you may realize that at this point, if we wanted to, we could do a hypothetical syllogism. Since the consequent here matches the antecedent there, we could go directly to pb then ab if we wanted to. I'm going to take the long route through the arrow introduction subderivation just for the purposes of illustration. So when doing this in English, we supposed that in fact Bill was a philosopher. That's an auxiliary assumption. 2 arrow eliminations gave us the following. 3 and 5 give us Bill is strange. 4 and 6 give us Bill is annoying. Both of those are error eliminations. Now we could exit that subderivation and generate the conditional from 5 to 7. If Bill is a philosopher, then Bill is annoying. And now, if you look at line 8, we have a formula with some constants in it. In this case, the constant is lowercase b. And we're going to replace all of those constants when we add a universal x quantifier. So this is different than existential introduction. In existential introduction, you can decide whether to do 1, 2, 3, or all of the constants. So this is different than existential introduction. If you have multiple instances of the same constant in existential introduction, you can choose whether to replace just some or all of them. Here, because of the second restriction, in moving from the constant to the quantified form, we need to replace all of the instances of the constant that we're concerned with. That's the force of the second restriction. So, what I can do is take PB arrow AB, and since our goal asks us to use a universal x quantifier, we'll do that, put in the parentheses, replace the first b with an x, and replace the second b with an x. And that's 8 universal introduction. So we've satisfied the second of the two restrictions on universal introduction. We should check and see if we satisfy the first restriction. This one says that the constant we're replacing with the quantifier, in this case, we're replacing b with x. That constant cannot occur in any undischarged assumption. Remember that assumption gets discharged when we use a subderivation rule on the subderivation that assumption started. So in moving from line 7 to 8, we discharge the assumption in line 5. It's no longer active, and we can tell that because the scope line ends. So it's okay that the constant b, which is the one that we're concerned with here, appears in line 5 because it gets discharged in the transition from line 7 to 8. So we're okay there. We do have two still active or undischarged assumption in lines 1 and 2, but b doesn't appear there, so we are perfectly fine on that restriction as well. So this is a perfectly good application of universal introduction, and we've completed the derivation. Let's see a couple quick examples of what happens if we violate the restrictions on universal introduction. Take, for example, the following derivation. There's a single primary assumption, and I don't have any goal in mind because we're just going to make a mistake here. But if you want an interpretation for what we're looking at there, imagine that the one-place predicate e is for is an even number, and the lowercase t constant is for 2. So what the primary assumption claims is that 2 is an even number. Now, if we do the following, add a universal x, replacing the constant t with the variable x, we might think that that is from one universal introduction. And if we ignore the restrictions, it does fit the form of the rule. We've taken a claim with a constant in it, we've replaced that constant and attached a universal quantifier. So it fits the form of the rule. But clearly, we can see in the interpretation, we shouldn't be able to go from 2 is an even number to everything is an even number. Well, what's gone wrong? Clearly we've made a mistake. And it's because we've violated restriction 1. How does it violate restriction 1? Well, the constant that we replaced in the transition from lines 1 to 2 is t. And restriction 1 tells us that the constant we're replacing cannot occur in an undischarged assumption. So in this case, it means that t can't occur in an undischarged assumption. But clearly, t occurs in the primary assumptions, which are never discharged. So we have violated restriction 1, and it's a big mistake. Here's another quick example. Take as a primary assumption the claim that everything is identical to itself. Or if you want to focus on numbers, every number is equal to itself. Now, we can do a universal elimination, removing the universal quantifier and replacing both instances of the variable x with a constant s. So you could think of that as 6 is equal to 6. That's one universal elimination. No restrictions to worry about there. Now we might then try to go back and call that a universal introduction. And again, if we ignore the restrictions, we've met the form of the rule, because we have a formula with some constants in it. We replaced at least one of them with a universally quantified variable. But remember, unlike existential introduction, which allows us to decide whether to replace some or all of the constants with the quantified variable, restriction 2 on universal introduction stipulates that the constant we're replacing, in this case it's s, must not occur in the final result, but clearly it does in line 3. So this is a mistake because it violates restriction 2. And of course that allows us to go from a true claim, every number is equal to itself, to a false claim, in 3, every number is equal to 6. So the upshot here is that these two restrictions allow us to prevent the hasty generalization fallacy. In putting restrictions on where the name comes from and how we have to eliminate it, we avoid relying on any particular claim and can generalize safely. So far we've seen 3 of our PD derivation rules dealing with the quantifiers. There were 2 pretty straightforward rules, universal elimination and existential introduction. We've just finished looking at universal introduction, which was a little bit complicated because it had some restrictions placed on it. The 4th of the necessary rules is existential elimination, and it is the most complicated of the 4. It involves 3 restrictions and a subderivation. Let's take a quick look at the rule form and then see how it works by example. So the rule is existential elimination. What it tells us is, if we have an existential claim at some point in a derivation, and we start a subderivation with a substitution instance of that existential as the auxiliary assumption, then after some work, make our way down to a formula Q, then that Q can be moved out to the next higher scope line, provided certain restrictions are met. Now let's talk abstractly about those restrictions, although it'll make more sense once we can see some examples. First of all, the constant that you use when making the auxiliary assumption cannot occur in any other undischarged assumptions. That is, in a sense, it has to be brand new to the derivation. Moreover, the constant you use in making that auxiliary assumption cannot occur in the original existential. And finally, it cannot occur in the Q result that you pull out of the subderivation. What's going on here with all these restrictions is that we want that constant A to be a totally arbitrary placeholder name for the sum x that is P. What's going on here with the constant A that we choose to start the subderivation is that we want it to be an arbitrary placeholder so that we know nothing about this A. It's just a name that's playing a role in the derivation. We use it for the course of the subderivation until we get to a Q that does not contain A. and then we can move that q out. So in a sense, that constant is born in the auxiliary assumption, and then it dies when we close the subderivation. Let's see how this works in practice. Consider the following argument. Two premises: all philosophers are strange, some philosophers are frightening. From this, we can conclude that some strange people are frightening. Now, how would we do that without symbols? Consider this. Now, notice that premises 1 and 2 don't name anyone in particular. Now, given that 1 is a universal, then we could choose any name, do universal elimination, and if that person is a philosopher, then that person is strange. That would be universal elimination, which we've seen. But for 2, we know that there's at least one philosopher who is frightening, but we don't have a name for him or her. So let's just arbitrarily choose a name. But in arbitrarily choosing a name, we want it to be totally random, not somebody we know anything about. In fact, we just need a name to go in the place so that we can carry on some reasoning. So let's start what amounts to a subderivation, and we'll indent to show that. Suppose Ralph is a philosopher who is frightening. That's an assumption. Now, we also know from line 1 that if Ralph is a philosopher, then Ralph is strange. That's a case of universal elimination. From 3, we get that Ralph is a philosopher. That's just a conjunction elimination. From 4 and 5, we get that Ralph is strange. That's just a conditional elimination. And from 3, we can get Ralph is frightening. Now with 6 and 7 put together, we get that Ralph is strange and frightening. Now, we don't actually know that there is a person, Ralph, who is strange and frightening. We don't even know to whom this name Ralph is referring. It's just in there as a placeholder in order to make our inferential steps. One last inferential step we can make under that assumption is to take the name Ralph out and just say someone is strange and frightening, or as I phrased it here, some strange people are frightening. This is just like an existential introduction. But now that we've gotten rid of the name Ralph, we can exit our subderivation, effectively discharging our assumption, and we get the conclusion based on just premises 1 and 2 that some strange people are frightening. I should say based on premises 1 and 2 and the process in 3 through 9. Now let's clear the English and see how it works with the symbols. Okay, so symbolically we might set up those two premises as primary assumptions in the following way. All x px, then sx, like we've seen before, for some philosophers are strange, and then some, and I'll just use y here for the sake of variety, some y, py, and fy for some philosophers are frightening, or there's at least one thing that is both a philosopher and frightening. Those would be our two primary assumptions. The goal here is to get to some x, sx, and fx. Some strange people are frightening. Let's put that down in as our goal formula. Now it seems pretty clear that that goal formula, some x, sx, and fx, at some point is going to be produced by an existential introduction. If we can get s constant and f the same constant, we could then do an existential introduction to introduce existential x. But the situation here is complicated by the fact that we have an existential in the primaries that we have to deal with. Now, we cannot just tear off that existential and put in a constant. That is, we couldn't do the following. and try to claim 2 existential elimination. This is a big mistake, and you can see why it's a mistake by thinking through it this way. Line 2 tells us that something is a philosopher and frightening, and then line 3 tells us that, say, A, or Albert, is a philosopher and frightening. But we don't know that based on line 2. We don't know that it's Albert. It might be Betty, it might be Fred, we don't know who it is. We just know that there is one. So rather than claiming that it has a particular name, we can start a subderivation in which we assume, for the sake of the subderivation, that it has a particular name by assigning it a constant. Now, to stick with the English example where it was Ralph, I'll use lowercase r as the constant. You can choose any constant you want, but you need to be careful to avoid choosing a constant that will run you into violating one of those restrictions. When we talk strategy in a later video, we'll talk about that in more detail. For now, we don't really have to worry too much about it. We'll choose the r. So my auxiliary assumption then is going to be PR and FR. We are going to have to be careful about the 3 restrictions on this rule, but let's not worry about them too much right now. We can come back and look at them in a bit. Now, given that there's a universal in line 1, I can do a universal elimination and get if PR, then SR. That's just one universal elimination. There are no restrictions or anything on that. I don't have to worry about it. Now, from the conjunction in 3, I can derive the PR on a line by itself by simple wedge elimination. Next, I'll use 4 and 5 together, an arrow elimination to get SR on a line by itself. And then I can get the FR out of line 3 by wedge elimination. And now all I need to do is put those 2 together, SR and FR. 6-7 wedge introduction. And you might be tempted at this point to say, okay, I'm going to exit the subderivation and then do the existential introduction to get the conclusion. But you cannot exit the subderivation until you've eliminated the constant that was introduced in the auxiliary assumption, in our case, the lowercase r. Well, how do we get rid of that? Typically, but not always, you get rid of the constant introduced here by reintroducing a new existential. So we've supposed the name Ralph, and we need to get rid of that name. Well, if, based on our auxiliary assumption, Ralph is strange and Ralph is frightening, then there's someone who is both strange and frightening. We can do an existential introduction, which carries no restrictions. And now we have in line 9 a formula that no longer contains the constant r, the one that was introduced as a placeholder name in the assumption of line 3. So now we are able to take that formula and exit the subderivation, which means that on the main scope line in line 10 we'll have the exact same formula. Notice that's exactly what happens here. As long as that Q meets this restriction and we've met the other restrictions, you can just move it out one scope line. And we call that, or the justification for that, is line 2 and the subderivation 3 through 9, existential elimination. Now, a couple of points worth noting here. First of all, we definitely need line 2 because we base the auxiliary assumption on the form of line 2. Without line 2, we could do that subderivation, but we wouldn't be justified in exiting it and claiming that some strange people are frightening. So we need the original existential, we need the subderivation, which starts with an instance and leads to a formula that no longer contains that constant. So both those pieces are necessary. Now, something that might seem a little strange is that it's called existential elimination. But we typically, though not always, we typically wind up with a formula that contains an existential. That's okay. The existential that's eliminated is the one in the original when we make the auxiliary assumption. In making that assumption, we eliminate that existential y in favor of a placeholder constant. But since that constant is just a placeholder, it must disappear by the end of the subderivation if we're going to be able to get out of it. And the typical way for it to disappear is that the last step in that subderivation is going to be an existential introduction. So even though it's called existential elimination, you often wind up with an existential in the result. It's really the original existential that gets eliminated in the auxiliary assumption. We'll look at some potential mistakes and violations of the restrictions in a moment, but I just want to emphasize one last time. Given the existential in line 2, we introduce an arbitrary placeholder constant in the auxiliary assumption, and so that constant is born right there in that auxiliary assumption. We use it to do some work and then remove it. It dies in a sense by doing an existential introduction, and then that allows us to pull the formula Q out of the subderivation without violating any of the restrictions. There will be other ways that the arbitrary placeholder constant might disappear at the end of the subderivation. We'll look at those in a little bit. That is, it won't always be another existential introduction, but it very frequently will be. We're going to take a look at 3 mistakes which help to illustrate why we have those 3 restrictions. We'll go in reverse order, starting with restriction 3 first. So consider the following derivation, and I'll give you a little interpretation as we go along that might help make it easier to see what the problem is. Some x mx, and you can think of that as there's at least one mother, and for all x, mx, then wx. All mothers are women. So I'm going to assume, for the sake of these examples, some strictly binary gender roles and parenting roles. There are plenty of good arguments to suggest we're being overly binary here, but set that aside for the time being. I don't have any particular goal in mind here, but I want to illustrate a mistake. So, in order to deal with the existential in line 1, we might start an existential elimination by making the assumption of a particular substitution instance of line 1. If someone is a mother, then suppose it's me. Gregory is a mother. That's perfectly legitimate. We haven't created any mistakes. That's perfectly legitimate. We haven't committed any errors yet. Now, from line 2, all mothers are women, we can get if Gregory is a mother, then Gregory is a woman. That's a universal elimination from line 2. Continue the subderivation a little bit longer. 3 and 4 and arrow elimination get us that Gregory is a woman. And again, there's really no problem here. Based on the assumption that I'm a mother, it follows from premise 2 that I am a woman. Now suppose we take line 5 and we move it out of the subderivation. And we try to call this 2, 3 through 5 existential elimination. It does basically fit the form of the rule. We assumed something that was a substitution instance of line 1. We did some work. We came down to a Q, and then we moved that Q out. That perfectly fits the form here. But clearly something has gone wrong because I, Gregory, am not a woman, and we've got 2 true premises. There's at least one mother and all mothers are women. We shouldn't be able to get to a false conclusion. What's the problem? Well, pretty clearly we've violated the 3rd restriction here. Restriction 3 says that the constant we introduce in the assumption, in our case g, does not occur in the q that we pull out, but very clearly it does. So we violated that restriction. And that restriction is designed to prevent a certain invalid inference or incorrect derivation from occurring. So we have to abide by that restriction. As a second example, consider this derivation. We'll start with just one primary assumption. For all x, there is some y such that Lxy, or everyone loves someone. Again, I don't have any particular goal in mind here. I just want to show how a mistake might be generated. Now, given that Formula 1 is a universal claim, we can apply universal elimination, remove the universal x quantifier, which leaves us with some y. We need to fill in the x position in the predicate with a constant, so let's choose f for Fred. And the y stays the same since we're just removing the universal. That's one universal elimination. Totally legitimate move. So from everyone loves someone, we get Fred in particular loves someone. Now, suppose we try to deal with the existential in line 2 by starting a subderivation for existential elimination. That means we need to assume a substitution instance of line 2. Suppose we pick f to replace the sum y. So we take the y quantifier off, we leave that f as is, and then where y appeared before, we stick in another f. This is a perfectly fine auxiliary assumption. We haven't broken any rules yet. What we've got now is that Fred loves himself. Take this as the next step. If Fred loves himself, then there's at least one x such that x loves him or herself. That comes from 3, existential introduction. Again, no rules have been broken here. Now let's suppose we treat line 4 as our q and we move it out one scope line to the main scope line. In this case, we're not violating restriction 3. The constant we're concerned with, f, doesn't occur in the q that we moved out. So we're not making the mistake that we made a moment ago. This is going to be a different mistake. But we'll try to call this 2, 3 through 4 existential elimination. It fits the form of the rule. We don't violate restriction 3, but there's still a mistake here. We shouldn't be able to get from a supposedly true claim that everybody loves somebody to somebody loves himself. It's perfectly possible for it to be true that everybody loves somebody while being false that someone loves themselves. So we've got a problem here. Where does the problem occur? So this, line 5, is a mistake. But why? Well, remember that the constant that we pick in making the auxiliary assumption cannot occur in the original existential. This was the constant we added in making the auxiliary assumption, but it already appears in the existential that we want to use for existential elimination. So we violate restriction 2 here. And in violating restriction 2, we wind up with a formula that doesn't actually follow from, is not actually derivable from, line 2 or line 1 for that matter. What's happening is, remember, we want the constant we add in the auxiliary assumption to be an arbitrary placeholder, meaning that we don't know anything about it, it's just a name. But because of the move we pulled from line 1 to line 2, we do have some special information about it, and we need to avoid that. That's the force of restriction 2. Note that had we chosen something different here, say B, we would avoid violating restriction 2, but we wouldn't be able to get to some x Lxx because the B would have to stay there. Or if we did it the other way, the F would have to stay there. That is, there's no way, if we do things correctly, to get to some x Lxx because you would have two different constants here. Let's look at one more potential mistake. All right, consider now this derivation. Suppose we have three primary assumptions. The first one, Gregory is a father. There's at least one mother, and no mothers or fathers. Again, bear with me as I be very binary about gender and parenting roles. So all mothers are non-fathers, or no mothers or fathers. We have an existential in line 2, and suppose we deal with that by assuming that it's Gregory that is a mother. Again, this is a legitimate assumption to make, but it's strategically bad because it's going to cause us to violate restriction 1 when we try to apply existential elimination. Bear with me while we play out the mistake. Now, from line 3, a universal elimination, which is totally unrestricted, we can say if Gregory is a mother, then Gregory is not a father. Again, no problems yet, except some strategic errors. And obviously 4 and 5 will give us Gregory is not a father by arrow elimination. 1 and 6 together will get us Gregory is a father and Gregory is not a father. That's just a simple conjunction or wedge introduction. You notice that we have a contradiction there, but technically there's nothing wrong with that. Now we can do existential introduction on that contradiction and say there is some x such that x is a father and x is not a father. Again, so far we haven't violated any rules, but here's where we're going to do that. We can move line 8 out and try to call it 2, 4 through 8 existential elimination. Certainly fits the form of the rule. We're okay with restriction 3 because g, the constant we introduce in the assumption, does not appear in the q that we move out. We're okay with restriction 2 because g does not appear in line 2, the original existential, but pretty clearly we must have a problem because we shouldn't be able to go from Gregory is a father, there are some mothers, no mothers or fathers, to there's at least one thing which is both a father and not a father. It's easy to see how these primary assumptions could all be true, but no matter what we do, this has to be false, and we don't want our derivation rules to lead us from true primary assumptions to false outcomes. So there's a problem. And you've probably already guessed and see what the problem is, but let's make it clear. This is a mistake. Right? We are violating restriction 1 because the constant that we introduced when we started with the auxiliary assumption for the existential elimination subderivation appears in an undischarged assumption. It's still active. The primary assumptions never get discharged. So 1 through 3 are undischarged and g appears there. The way to look at this is, in the assumption of line 4, we want to introduce a brand new constant, one that is born there and eventually dies before the end of the subderivation, but that constant g is already in active use from line 1, so we should not have picked g. Had we picked something else, say an f, we could proceed as we did until this point. We wouldn't be able to get fx and not fx because we would have g here and a lowercase f here. So we wouldn't be able to generate some x fx and not fx if we abide by that restriction. And so that's just an illustration of how violating that restriction can get us into trouble. Now, as you can see, we've got 4 basic derivation rules for the quantifiers. The first 2, universal elimination and existential introduction, are pretty straightforward. I call those the friendly rules. They have no special restrictions. They're not terribly complicated. They should be rather intuitive. The third and fourth rules, universal introduction and existential elimination, are a little bit more complicated. They're unfriendly rules. Universal introduction has 2 restrictions. Existential elimination has 3 restrictions and a subderivation. In subsequent videos, we'll talk about how to strategize using these rules for different derivational situations. These are the only 4 rules we actually need to deal with the quantifiers. However, we can introduce one equivalence rule that will make dealing with certain things much easier. And we'll do that in the next video.